Hello everyone, welcome back. In the last class, we were discussing about the position of hydrogen in the periodic table, and I have mentioned that the position of hydrogen in the table is debatable because it resembles both the alkali metals as well as the halogens in certain respects, and in certain other respects, it is quite different from the alkalis as well as that of the halogens. So let us see some of these properties where hydrogen resembles the alkali metals as well as the halogens, and where it differs from the properties of these two groups of elements. Now, let us first see some reactions, some properties where hydrogen resembles the alkalis and the halogens. If we see the electronic configuration of hydrogen, it has only one electron, so only one shell, only one orbital, and in that single orbital there is a single electron. The general configuration, the outer electronic configuration for the alkali metals is NS1, and for the halogens, the general outer electronic configuration is NS2 and P5. This is for hydrogen, this is for the alkali metals, and this is for the halogens. These are the configurations. Now, if we just see the electronic configuration of hydrogen, it has only one electron in its valence shell, which is the first shell itself. Just like this, alkali metals also have one electron in the s orbital of the valence shell. So in this respect, both alkalis as well as hydrogen have only one electron each in their valence shells, and that too in the s orbitals. Now, if we see the configuration of the halogens, they have 7 electrons in the valence shell. They are 1 electron short of attaining the octet state. So if these halogens, they gain 1 electron, they will attain the stable configuration of the next group of elements, that is the noble gases. So these are 1 electron short of attaining a stable noble gas configuration. Hydrogen, if it attains 1 electron, it will attain the configuration of helium. The configuration of helium is 1s2, it has 2 electrons. So if hydrogen accepts 1 electron, it will attain a stable configuration of helium, which is also a noble gas. So in electronic configurations, hydrogen resembles the alkali metals in one respect, in the other respect, it resembles that of the halogens also. Hydrogen can lose 1 electron and form a unipositive ion like this. Just like this, alkali metals, since they have only 1 electron in their valence shell, whenever they undergo chemical combinations, they will always give out 1 electron and form a unipositive ion. For example, sodium gives out 1 electron, forms sodium ion. Like that, potassium also forms a unipositive ion by losing 1 electron. So in certain reactions, hydrogen will give out 1 electron and form a proton like this with one single positive charge, like the alkali metals, which always give out 1 electrons during the reactions. Again, hydrogen can also accept 1 electron to attain this configuration. So by accepting 1 electron, it forms a uni-negative ion, in anion. Just like that, halogens also, since they are deficient in 1 electron, they will accept 1 electron and form uni-negative ions, like this chloride ion or fluoride ion. So like the alkalis, it can give out 1 electron and form a uni-positive ion, and like the halogens, it can accept 1 electron to form a uni-negative ion like this. Hydrogen can react with non-metals also. All the alkali metals, they react with non-metals. So just like the alkalis, hydrogens can react with non-metals to form oxides or sulfides or even halides. Just like that, halogens, they can react with metals. When halogens react with metals, they form halides. Like that, hydrogen can react with metals also to form hydrides. So like the alkalis, hydrogen can react with nonmetals, and like the halogens, hydrogen can also react with metals. So these are properties in which hydrogen resembles both alkalis as well as the halogens. But there are certain other properties where hydrogen differs from alkalis as well as the halogens. For example, the oxide of hydrogen, H2O, is neutral. But the oxides of metals, the alkali metals, they are basic in nature. Oxides of the halogens, which are nonmetals, they are usually acidic in nature. So hydrogen forms a neutral oxide, alkali metals form basic oxides, whereas halogens form neutral oxides. So in the formation of oxides, hydrogen differs from both alkalis as well as the halogens. Hydrogen is a nonmetal. Alkali metals, they are metals. So unlike the alkalis, hydrogen is a nonmetal. It is a nonmetal like the halogens, but the halogens are very highly reactive. But hydrogen is very less reactive at room temperatures. So in its reactivity, it differs from that of the halogens. In its metallic nature, it differs from that of the alkali metals. So these are again some properties where hydrogen differs from both alkalis as well as the halogens. So since it resembles both these groups of elements in certain respects and differs from them in other respects, it is more appropriate and more justified to assign a separate position to hydrogen in the periodic table without associating it with any group. That is why, if you see in the periodic table, hydrogen will be placed at the dope of group 1, on the left side at the dope of group 1, but it is separated from group 1 also to indicate its distinctive nature. Now, if we see the physical properties of this hydrogen gas, it is a colorless, odorless, and tasteless gas. It is combustible but does not support combustion. It is the lightest element known, so it is lighter than air and it is insoluble in water. So these are some physical properties of hydrogen. If we look at the chemical properties, just as I have mentioned in the previous class, hydrogen in the molecular form is very less reactive under ordinary conditions or at room temperatures because the bond between the two hydrogen atoms, this bond is very strong. It has a very high bond dissociation enthalpy and therefore hydrogen is very less reactive. However, under elevated conditions of temperature and pressure or in the presence of catalyst, hydrogen can react with a lot of compounds, with metals as well as non-metals to form different types of compounds. Another thing to remember is that once this hydrogen molecule is broken up into atoms, we get atomic hydrogen, which is very highly reactive. So molecular hydrogen is less reactive, but atomic hydrogen will be very highly reactive. Now let us see some chemical reactions of this hydrogen. The first is the reaction with halogens. Hydrogen, it reacts with halogens in the order fluorine, chlorine, bromine, and iodine. This means that reactivity of the halogens with hydrogen is in this order. That means fluorine reacts fastest with hydrogen, next is chlorine, and the least reactive will be iodine. Now, suppose we take hydrogen and take one of these halogens, then we get a halide like this, a hydrogen halide. So if we take fluorine, then we will get hydrogen fluoride. If we take chlorine, we will get hydrogen chloride, which is also called as hydrochloric acid. Then if we take bromine, we will get hydrogen bromide. And if we take iodine, we will get hydrogen iodide. These halides of hydrogen are called as the hydrogen halides. Now, reactivity of fluorine is the highest for these halogens when they react with hydrogen. So Fluorine can readily react with hydrogen even in the dark. But if we react chlorine and bromine with hydrogen, these reactions they take place when heated. So this has to be heated. And the reaction with iodine will take place only in the presence of a catalyst. We have to heat it, as well as we have to include a catalyst to speed up the reaction. Reaction with oxygen. Hydrogen reacts explosively with oxygen to form water. And this reaction is highly exothermic. So a lot of heat will be generated when these two elements combine to form water. The third reaction is the reaction with dinitrogen. On reacting with nitrogen, ammonia will be formed. And this reaction forms the basis for Hepbur's process for the manufacture of ammonia, which is a very important chemical compound. Now, with metals, hydrogen can also react with metals to form different types of hydrates like lithium hydride or sodium hydride. These are the different types of hydrides that are formed when hydrogen reacts with metals. And all of these metals will be ionic or electrovalent. Hydrogen also reacts with many organic compounds in the presence of catalysts to give useful hydrogenated products of commercial importance. For example, hydrogenation of vegetable oils using nickel as catalyst gives edible fats such as margarine or vanaspati ghee. So organic compounds like oils, which are unsaturated compounds, they are hydrogenated. They are treated with oxygen in the presence of catalysts such as nickel. These oils, they are converted into ghee or solid vegetable ghee. In the process, unsaturated compounds are converted to saturated organic compounds. And this process is called as hydrogenation. Now, some uses of hydrogen. If we see the uses of hydrogen, there are so many uses of this hydrogen. Let us see some of them. One, it is used for hydrogenation of vegetable oils, just as we have seen here. Then the second one is for manufacture of methanol and ammonia. Methanol in alcohol and ammonia, these are very important chemical compounds. And hydrogen is used for production of these two compounds. It is also used as a rocket fuel in space research and for reducing heavy oxides to metals. It is used in fuel cells for generating electrical energy. And it has many advantages over conventional fossil fuels. It does not produce any pollution and release greater energy per unit mass of the fuel. That means hydrogen has a very high calorific value. A small amount of it can generate a lot of energy. So those are some uses of this dihydrogen. Now, compounds of hydrogen, binary compounds of hydrogen with other elements are called as hydrides. And these hydrides, they are classified into three categories. The first one is the ionic or salt-like or saline hydrides. Ionic, salt-like or saline hydrides. These ionic or saline hydrides, they are formed when hydrogen combines with group 1 and group 2 elements. That means the alkali and alkaline earth metals. Except beryllium and magnesium, all the alkali metals and the alkaline earth metals, they combine with hydrogen to form these ionic or saline hydrides. Examples like sodium hydride or lithium hydride, calcium hydride, all of these are hydrides formed from group 1 and group 2 elements. So these are ionic or saline in nature. Now these saline hydrides, they are crystalline, they are non-volatile, and they are non-conducting in the solid state. However, in the molten state, they conduct electricity, and on electrolysis, they liberate dihydrogen gas at the anode, which confirms the existence of hydrogen ions in these halides. They also react violently with water, producing dihydrogen gas. So if we take a saline hydride like sodium hydride, this react with hydrogen to form hydrogen gas. All these saline or ionic hydrides, they will react with water to form hydrogen gas. The next type of hydrides is the covalent or molecular hydrides. Elements of p block form these covalent hydrides. So elements from the p block, that means from group 13 to group 17, these elements, they will combine with hydrogen to form covalent or network hydrides. For example, methane or ammonia or even water. These are examples of covalent or network hydrides. Now, molecular hydrides are further classified into the following types. The first one is electron deficient hydrides. Electron deficient hydrides which have lesser electrons than required for writing their conventional formulas, that is their Lewis structures. For example, diborane B2H6 is an example of these hydrides which are electron deficient. All elements of group 13 form electron deficient hydrides. Being deficient in electrons, they accept electrons and therefore act as Lewis acids. Let us see the example of BH3. In BH3, the boron atom here has only 3 electrons in the valence shell. Now, these 3 valence electrons, they are shared with electrons from the 3 hydrogen atoms, and boron trihydride is formed. Now, if we see this structure, the boron atom will have only 6 electrons, which is too short of the octet. Every atom tries to attain the octet state. But in this compound, boron has only 6 electrons, not 8. Therefore, it is deficient in electrons. So, this type of hydrides are called as electron deficient hydrides. And these are formed by elements of group 13. All the group 13 elements will form these electron deficient hydrides. Since they are deficient in electrons, they will be able to accept electrons. Those which accept electrons, they act as Lewis acids. So, all these hydrides of group 13 elements which are electron deficient, they will act as Lewis acids. Then the next one is the electron precise hydrides. Those which have required number of electrons to write their conventional formulas. Elements of group 14 form electron precise hydrides. So if we take CH4, carbon is in group 14, it forms the hydride CH4. If you see the structure of CH4, carbon has 4 valence electrons. These are shared with 4 hydrogen atoms, like this. So in CH4, the carbon has 8 electrons. The octet is complete here. So these kind of hydrides are called as electron precise hydrides. And these are formed by elements of group 14. Then the next one is the electron-rich hydrides, which have more electrons than required to write their conventional formulas. Elements of group 17, 15 to 17 form electron-rich hydrides. For example, if we take nitrogen, an element from group 15, it forms NH3, which is the hydride of nitrogen. In NH3, the nitrogen atom has 5 electrons in the valence shell, only 3 are shared with 3 hydrogen atoms, and therefore it has a lone pair which can be donated. So this kind of hydrides, they are said to be electron-rich hydrides, and since they have lone pairs of electrons which they can donate, they act as Lewis bases. That is all for today. We will continue in the next class.